Okay, so now we are going to add vectors that are moving perpendicular. So perpendicular vectors, what happens when we add them together? Okay, first of all, perpendicular, another way of saying that is that the two vectors are at right angles. So perhaps one is moving straight up or maybe straight north for 3 meters, and one is moving to the east or completely horizontal for another 4 meters. So the question is, what happens when you add 3 and 4 together? So this is where we get some weird behavior. So tip to tail would say first vector 3 up, second vector, I'm going to take its tail, put it at this tip. Oops, that's supposed to be a straight line. That's 4 meters. Now, this is for perpendicular or right angles, so I know that this is 90 degrees, like that, and my resultant is going to be straight across here from the first tip, from the first tail to the last tip, from the start to the end. So going up and over is like going across. So we're trying to find R. Now, this is a right angle triangle, so we've got some things that are working for us, namely Pythagoras' theorem. So if this is a right angle triangle, this side here, opposite the right angle, is the longest side, called the hypotenuse. Sometimes we label it C, other ones we'll call A and B, and Pythagoras' theorem says that C squared equals A squared plus B squared. So in our triangle, we're looking for the hypotenuse, the longest side, so R is like C. So R squared is equal to, and the other sides are like A and B, 3 squared plus 4 squared, which is 9 plus 16, which is 25. So we know that R squared equals 25. But nobody cares what R squared is, we want to know what R is. So we'll take the square root, R is equal to the square root of 25, which is 5. So 3 plus 4 equals 5 in the strange world of perpendicular vectors. Note that the length of our resultant vector is 5 by using Pythagoras' theorem. 3 squared plus 4 squared equals 5 squared. This is a good triangle to know. It's called the 3, 4, 5 triangle, or Carpenter's triangle. It can give a right angle here. Okay, so that's great. We know the length of our vector, but remember vectors have magnitude, which we found, and direction. So we haven't given the answer for the vector until we know both of these things. So now we need to find out what direction it's moving in. So again, we have a right angle triangle, so that's great because we can use our trig ratios, SOHCAHTOA, or SOHCAHTOA, whichever you like. So what SOHCAHTOA says is that you pick an angle, whichever angle you're interested in the triangle. Let's say we pick this one here. So then you label your triangle. Opposite the 90 is always called the hypotenuse. Opposite whichever angle you work with is called opposite. And then the remaining side would be the adjacent. So this SOHCAHTOA says that the sine of our angle is equal to the length of the opposite side divided by the length of the hypotenuse. And the cos of the angle is equal to the length of the adjacent over the hypotenuse, and tan is opposite over adjacent. adjacent. So let's go over to our triangle and we'll pick an angle to work with. I'm going to pick this angle right here. So from this angle's point of view, this side is the opposite. This is opposite the 90, so this is always the hypotenuse. And this angle right here will be the adjacent. So I'd like to work with my given numbers rather than my found numbers. So I'd like to work with O and A, which means that I'm going to choose tan because it has O and A. So tan of my angle, which I'm trying to find, is equal to opposite over adjacent. So opposite is 4 over adjacent, which is 3. So I know the tangent of the angle, so I need to work backwards, take the inverse tangent of that. Inverse tangent of 4/3 equals. So I'm going to need to pull in my calculator. I want the inverse tan of 4/3. So inverse tan is the tan to the -1 here. So inverse tan, also called arctan, 4 divided by 3. And I'll ask it what that is. 53.1 degrees. Okay. So right here we know that the angle is 53.1 degrees. Okay, so I guess if this is north, then this is east, and looks like my resultant has rotated towards the east. So I would say R is equal to 5 meters at 53.1 degrees east. That's the direction I've rotated from, but we say of north, east of north. It's a perfectly 100% correct answer for this question. So if we decide to work slightly different, we can get an answer that appears different, but it's really not. So we took 3 meters north and 4 meters east and came out with 5 meters at this angle, east of north. So what happens if we decided to add our vectors in the opposite order? So what if we had started here and gone 4 meters to the east and then 3 meters? Well, you can see here that we would have gotten the same length here, 5, but we would have been working in this green triangle. So chances are we would have found this angle right here. Now, you can see from this drawing, since these are at 90 degrees, that theta is going to be equal to 90 minus 53.1, or what is that, 36.9 degrees. Okay, but we wouldn't know this if we'd just been working with the green triangle. So if we were just working with the green triangle, then again we would label the triangle. This would be O, and this would be A, and then we would take the tan, we would write the tan of theta is equal to O over A, and we would take the inverse tan of 3/4. Okay, and just so you don't think that I'm messing with you, I'm going to show you that the inverse tan of 3/4 does actually come out to be equal to 36.9 degrees. Just as predicted. So now we would be set at answering that we're going 5 meters And we now know this angle right here, 36.9 degrees. So we would answer 5 meters at 36.9 degrees, and now we seem to have rotated from east towards the north, so north of east. Okay, compare this to the previous answer, which is 5 meters at 53.1 degrees east of north. And let me just show you that that's the 53.1, and this is the 36.9, and of course these two would add up to 90 degrees. Oh, that's not a good color. 90 degrees here, right? So these two together add to 90 degrees, and it's just two different ways of describing the same vector. So both of these answers are completely and 100% correct.